About 14 billion years ago, an explosion of a tiny volume created a hot and dense soup of elementary particles. This event, known as the Big Bang, is believed to be the beginning of our universe. Since then, the universe has been continuously expanding. As it expanded, it gradually cooled down and gave rise to structures such as atoms, molecules, stars, planets, galaxies. Scientists are trying to understand how the infinitely small gave rise to the infinitely large. In order to go back in time, it is necessary to explore the infinitesimal world. Understanding the structure of matter and the forces governing it is critical to understanding the history and the future of our universe. Scientists are building increasingly bigger devices to explore increasingly larger worlds, as well as smaller and smaller worlds. In the laboratory, they're trying to reproduce the reactions which take place in the stars or those that occurred at the origin of the universe.
Welcome to the Faculty of Science of the University of Orsay. I am Guidal, researcher at the Institut de Physique Nucléaire of Orsay. Before presenting to you the activities of research of my group, let us first meet Faisal Azayez, who is the director of IPN Orsay. Faisal, bonjour. Can you tell us a few words of introduction about IPN Orsay?
Bonjour Michel, of course, with great pleasure. So IPN stands for Institute of Nuclear Physics, and it's, as many people know, one of the largest nuclear physics laboratory in Europe. Actually, it's the largest one in France. It has a long history, and it has been built by a Nobel Prize, Frédéric Joliot. From the beginning, the tradition was to carry research on the field of nuclear matter, nuclear physics. For that reason, mainly, the main research activity understanding nuclear. There is also another important activity, and this is related to your research field, Michel. It's about understanding hadrons, typically what is the structure of nucleons. Last but not least is a famous reputation that we have in the Institute to be a well-known accelerator developer and accelerator builder. So we have a division that has gained a lot of expertise on designing and building accelerators. I would like just to mention this is a proof, or I would not say a living proof, but it's really a visible proof of how much accelerator we have been building here and elsewhere. This is what remains from a dismantled facility dedicated to heavy ion acceleration and study. So this is a portion of it, and this is a linear accelerator, one of the first one, accelerating heavy ion. So this is the main legs of our institute.
Thank you very much, Faisal, for these few words of introduction. Let us now immerse ourselves in the structure of matter. We aim at understanding the structure of the proton. To understand what that is about, let me take you on a little journey inside the structure of matter. Most of the things that surround us can be understood as being made of molecules. Molecules are an assembly of atoms. For instance, let's take this tennis ball. It is made essentially of rubber with air inside. Rubber is principally made of a molecule called isoprene, which is an assembly of carbon and hydrogen atoms. These atoms are bound together by the electromagnetic forces of the same nature as the electric and magnetic forces with which we are familiar in our daily lives. The atoms are themselves composite. They are composed of a nucleus surrounded by a cloud of electrons orbiting around the nucleus. The electrons are all those little green particles all around me. Once again, the electromagnetic forces hold the atom together. Continuing our journey inside the infinitesimal world, we now reach the substructure of the nucleus. It is made of nucleons. Nucleons come under two forms: protons, which have an electric charge positive, and neutrons, which are neutral electrically. Protons are here in red, and neutrons are here in blue. The number of protons and neutrons in a nucleus is what differentiates between different nuclei. For instance, a nucleus of carbon is made of 6 protons and 6 neutrons, while a nucleus of hydrogen is made of only 1 proton. For a long period of time, we thought that nucleons were the ultimate constituents of matter, that they had no substructure. For about 40 years now, we know that they are also composite and that they are made of another class of subparticles, the quarks and the gluons. A nucleon is a very complex object. The quarks, which are the particles of matter, are confined in a very tiny volume, which is about 100,000 times smaller than the size of an atom. The gluons are the vectors of the so-called strong force. The gluons keep the quarks confined in this tiny volume. The strong force is a very different force than the electromagnetic one. As there is an electric charge, there is a color charge. It comes under 3 forms: red, green, and blue. Quarks and gluons are constantly interacting. They even create new particles, which are called antiquarks, the antiparticles of the quarks. Sometimes the nucleon can appear as an assembly of 3 quarks, sometimes as a soup of quarks, antiquarks, and gluons. All this depends on the scale with which we probe the nucleon. This is this new realm that we are trying to understand and which is the subject of research of our group. How do the microscopic properties of the protons and the neutrons, their mass, their electric charge, emerge from their inner constituents, the quarks and gluons? 99% of the mass of the visible universe comes from the protons and the neutrons. It is therefore a fundamental issue to understand their inner structure and their properties. I'm now back in my office, and I'm going to give the floor to my colleague Sylvia Nicolai, who is going to explain how, in practice, through experiments, we investigate the inner structure of the proton. Bonjour Sylvia.
Bonjour Michel. Oh, he's gone. To understand the behavior of the quarks and gluons that compose a nucleon, we use electrons. By smashing a proton or a neutron with a high-energy electron beam and recording the properties of the particles produced in the collision, we obtain information on the dynamics of the constituents of matter. Our group performs its research at the Jefferson Lab in the USA. Here, the accelerator produces an electron beam matching the requirements in terms of energy and intensity that are necessary to investigate the structure of nucleons at the quark level. The beam is delivered to an experimental hall, where it collides upon a target. The particles emitted after the interaction travel through detectors that convert into electric signals the signs of their transit, such as their energy deposit in scintillating material. The signals are then analyzed to retrieve the properties such as electric charge, energy, direction of the particles that produce them. The results obtained can then be interpreted with the aid of theoretical tools. Our experimental research takes place in the Hall B of Jefferson Lab, home of the CLASS detector. Its large angular coverage and high-quality particle identification capabilities make CLASS the optimal device for our studies on the structure of the nucleon. Here, you can see the future version of the CLASS detector, CLASS 12. It will replace the existing CLASS in 2014, when the accelerator will be upgraded to reach a maximum energy twice as much as the one currently produced. The European members of the CLASS collaboration are involved in the construction of various detector subsystems for CLASS 12. The French groups of CEA-Saclay and our group of IPN-Orsay in particular are focused on the central detector, which will measure particles emitted at large angles. Here we are, inside the central detector of CLASS 12. It is a cylinder of roughly 1 meter of diameter and 1 meter in length, filled up with various detector subsystems, each having a different specialization. For instance, the micromegas detector that you see here, studied at Saclay, will measure the trajectory of charged particles. Our group is in charge of the central neutron detector that you see here in purple. It will identify neutrons emitted at large angles. The I3HP funds have contributed to our R&D studies, allowing us to define the optimal design and constituents of the detector.
This film has focused on the particular research conducted at IPN Orsay. However, the work package at I3HP has a much larger scope. It involves around 20 institutes from 7 European countries working on theory and particle detector research and development for other accelerators, such as the CERN in Geneva. Scientific progress is often the result of bringing together the ideas, knowledge, and expertise of different individuals or groups from different origins. By stretching across borders and by supporting non-profitable international projects, the European 7th Framework Program conducts research that otherwise could not be carried out by one country alone. It provides an excellent environment for scientific progress and the nurturing grounds for new projects and ideas. The large, complex apparatus and infrastructures, which are built to explore the infinitely large or infinitely small worlds, push the frontiers of technology and will ultimately impact and serve the industry and our daily lives. Fundamental cutting-edge research helps educate and train the future engineers and applied scientists of our societies, and more importantly, it gives them the taste for discovery.